it would be interesting to compare carboxylic acid derivatives in nucleophilic acyl substitution reactions. But before we do that, well, obviously these are the carboxylic acid derivatives, okay? Acid anhydride, if L or Y is X. Acid anhydride, if Y is a carboxylate. If Y is OR, it's an ester, or if it's NR2, then it would be an amide. Now, it would be important, obviously, and to recall the constituents, if you like, or the parts of the nucleophilic acyl substitution reaction. Remember that nucleophilic acyl substitution reaction begins with an initial addition step, an initial nucleophilic addition step, followed by elimination of the leaving group. So if one would compare these carboxylic acid derivatives, it would be very, very important to consider the factors that enhance the nucleophilic addition step, and obviously also, in addition to that, the factors that enhance the subsequent elimination step, the departure of the leaving group. Now, a nucleophilic addition reaction or the nucleophilic addition step is facilitated by the electrophilicity of carbon. In other words, the most electrophilic carbon of these carboxylic acid derivatives should undergo fast nucleophilic addition step. So what improves electrophilicity? Well, they are all carbonyl compounds, so they all have inductive effect or inductive withdrawal by oxygen, and also they all have resonance withdrawal because they all contain this acyl group. All of them are carbonyl groups. So carbon of the carbonyl group in all of them is electrophilic due to inductive effect and resonance. So the difference really will only be exerted by Y, if you like, the other group, which makes them derivatives of carboxylic acid. So X here, halogens, for example. Of course, halogens are electronegative atoms, so they are more electronegative in general than carbon, so they pull electrons toward themselves in this CX bond. Oxygen is also more electronegative than carbon, so it pulls oxygen electrons toward itself in this CO bond, but also oxygen has lone pair, so oxygen not only it can withdraw by inductive effect, but it can also donate by resonance. And we have seen this already before in the chemistry of benzene, that hydroxyl groups or alkoxy groups behave as electron donating groups. That's because of the presence of a lone pair on oxygen. They are electron donating groups by resonance more than electron withdrawing groups by inductive effect. That's because their resonance is not problematic or strong. It is actually stronger than their inductive effect. Oxygen here also in esters is more electronegative than carbons, okay? But here the presence of another carbonyl group makes actually a difference in reactivity, as we will see. Nitrogen is the least electronegative atom, so it pulls electrons toward itself, actually, yes, but the least. In fact, nitrogen is a good electron donor. Relative to nitrogen, is a much better electron donor because it is less electronegative. Now, therefore, electrophilicity is a very important issue in this regard, okay? So let's write that down. Electrophilicity is a very important issue. The most electrophilic carbon of the carbonyl group would be the most reactive in the nucleophilic addition step only. Now, the second step of the nucleophilic acyl substitution reaction is actually elimination. So anything that makes that departure of the leaving group favored would make the corresponding carbonyl compound, the corresponding carboxylic acid derivative more reactive than another. So therefore, leaving group ability, that's another important issue that we should discuss. A good leaving group obviously should be a weak base, it should be a stable ion. A good leaving group again should be a weak base and unstable ions. So the most, or the weakest actually, the weakest base would be the best leaving group. The most stable ion, if you like, would also be the best leaving group. Another way to judge leaving group ability is to look at the corresponding acids or the conjugate acids, to look at the pKa. Obviously, a strong acid should produce a weak conjugate base, therefore a stable ion, therefore a good leaving group. A very weak acid should produce a very strong base, therefore an unstable ion and a very poor leaving group. Now, X halogens are more electronegative than oxygen. We'll talk about details in due course, but in general, halogens are more electronegative than oxygen or nitrogen, so therefore their inductive effect or withdrawal is actually higher. So X is more electronegative than oxygen. Oxygen, of course, still is an electronegative atom, but less than X in general. Nitrogen is even less electronegative than oxygen. So without going into details, acid halides, for now, we'll go in details shortly. Acid halides are the most electrophilic. The most electrophilic carboxylic acid derivative are actually acid halides in general, followed by acid anhydrides, followed by esters, and last amides. So these are the most electrophilic acid halides. Amides are the least electrophilic, so they should be the least reactive in nucleophilic acyl substitution. Now X minus as a leaving group, this should be the best leaving group versus NR2 minus, and here of course OR minus as a leaving group, and here the carboxylate as a leaving group. Amongst these leaving groups, X minus or halides in general are the best. So these are the best leaving groups because they are the weakest bases, most stable ion, therefore best LG, best leaving group, if you like. Now amides come obviously from amines. Amides are actually very strong bases. They are unstable ions. So amides are strong bases. Actually, they are the strongest bases. They are the least stable ion. Therefore, they are the poorest, or the worst, if you like, leaving groups. Now, as a result of this, and because acid halides are the most electrophilic and they contain the best leaving group, they should be the most reactive in nucleophilic acyl substitution reactions. So acid halides are the most reactive in nucleophilic acyl substitution reactions, whereas amides are the least reactive. So this is like a reactivity scale. Acid halides are the most reactive in nucleophilic acyl substitution reactions, followed by acid anhydrides, esters, and finally amides. Amides are the least reactive. Again, that's because they contain the least electrophilic carbon. That carbon of the carbonyl group is the least electrophilic, and the amide ions are the worst leaving groups. We will talk about details very shortly.